Okay, Module 8.
Hi, John Mark.
Hi, John Mark. Here's our schedule. We're looking at our midterm exam in 2 weeks, and then our STEM day after that. All right, what is energy? We're going to watch a video.
Science. In this video, I'd like to talk about different forms of energy. Up first is mechanical energy. As this roller coaster moves up this hill, energy is used to overcome the force of gravity. You lose energy, but the roller coaster gains potential energy. At the top of the hill, the coaster has potential energy. As the coaster moves down the hill, it now has kinetic energy, or energy of movement. So mechanical energy is the total of the potential energy plus the kinetic energy. Nuclear energy is energy stored in the nucleus of an atom. When large atoms such as uranium or plutonium are split into two smaller atoms, in a process called fission, energy is released. Nuclear power plants use this process to help create energy. Chemical energy is the energy of chemical reactions. Chemical energy of a chemical substance can be transformed to other forms of energy by a chemical reaction. A chemical reaction is one chemical substance is transformed into another. Examples of chemical energy include batteries, burning gas in a car, and fireworks. Light energy is the form of electromagnetic radiation, which means it has electric fields and magnetic fields vibrating back and forth very quickly as a wave. Visible light is the portion of this radiant energy that we can see. Examples of light energy include light bulbs, a fire, or a lamp. Sound energy is the form of energy that is associated with vibrations of matter. It is a type of wave, which means it needs an object to travel through like air or water. When you play a guitar, the strings vibrate and cause waves to travel to your ear. And finally, electrical energy is the energy that is caused by moving electric ions. Since the electric charges are moving, this is a form of kinetic energy. The faster the electric charges are moving, the more electrical energy they carry. Electrical energy powers most of the appliances and gadgets in your house. So there we go, several different types of energy.
Okay, so that tells us types of energy, but the question still remains, what is energy? So here it is, the official definition we'll be using. Energy is the ability to do work. Okay, we're not talking about going to work. We're talking about actual work. Scientific definition of work is if something gets moved. All right, so if I move this like this, I just did work. Okay, because I moved it. But if I push against this wall of the church, I can push really hard, and it's not moving, no work is being done. Okay, because it didn't move. So that's the official definition of work. Okay?
You did put energy into it.
So my body moved a little bit, so I had some work being done on my body. My muscles, but not on the wall. No work was done on the wall. All right, so there are two general types of energy, which he did mention in the video. The first one is called kinetic energy. Yes?
So if you're working out, is that not technically working? Really?
If you're moving something, you're moving your muscles, then that's work. Yeah, working out. It's just not necessarily talking about a job you go to, although you go to your job, so you're moving. Okay. Kinetic energy means moving. Something's moving. All right. So, like for instance, I'm not going to use your calculator. Let's use something that won't get hurt. No. Okay. So this is my little bag that holds my little pointer, right? So it's sitting right here. All right. So now it is, not moving, right? So it's sitting there. So what it's experiencing right now is not kinetic energy. It is experiencing potential energy. What kind of potential energy does that little thing have right there?
If it were to move, it would.
Hey, what if I do this?
Have more energy. Free fall.
There it goes, free falling, right? Yeah. So it moved. That means it had kinetic energy, meaning work was done. What was it that pulled it down? Gravity, which is a force, right? All right, so we have have kinetic energy and potential energy. Looking at a roller coaster, didn't we last time we were together put a little roller coaster together? Was that the last time? We,
It was two.
or was it 2 times ago? Okay. We made the little roller coaster, you know. So we can see at the top, before the little car was let go, it was sitting there still, and you had to give it a little push. So it was potential energy. You gave it a push. What pulled it down through the whole thing? It's called a roller coaster, because gravity is doing the trick. And if you have enough of the force pulling it down, you can make it do something, go against gravity for a second, right? Do a loop-de-loop or something like that. We had a couple of failures on that one, right? So you can see our potential energy is 100%. Our kinetic energy is 0. As we go down, look how we're exchanging. 50% potential, 50% kinetic. Then we get to a point where it's 100% kinetic. And now it's going to go back up. So it kind of slows down, gets back up. 75-25. So there's always that exchange going on here. I have it now in one that's moving. Here we go. Watch how kinetic, physical swap sides here. Kinetic all the way up. And now we're going to see some potential. It should be all the way up. So our little scale right there is changing depending on. So the moving is when the kinetic energy should be up. So what are we looking at? Okay, yeah, so if it's blue, that means it's completely potential. And it's also telling us a speed here. So as long as it's moving, there's not really a lot of potential energy. When it stops it for a moment, we get some. Okay. So kinetic energy, we have an equation that you need to write down. I believe there's a box to write it down, yes? It says equation 8.1. Oh, it's written down for you? KE, so kinetic energy equals 1/2 times mass times velocity squared. Okay? So here we have m times v2 over 2. We could put those together right instead of the 1/2 right there. That 2's just on the bottom, you get that? The units are in mass, kilograms, and then velocity in meters per second. So we're looking here. This kid's throwing a baseball, and so when the ball's moving, of course, it is being affected by kinetic energy. We know the ball has a certain amount of mass, and we know that this kid can throw it at a certain velocity. Okay, before we move any further to get into an example problem, what is a joule? It turns out a joule is the way we measure energy. Energy is measured in a unit called the joule, named after this guy, Dr. James Joule. If we have large energy amounts, they're typically measured in something called a kilojoule. It's really big, okay? And our unit is going to be this. A Newton meter is going to be a joule, okay? So we'll call it, instead of writing all this down, we'll just call it a joule. So that's an energy unit. All right, so here's our first example. You have an example there? Mm-hmm. A 1,200 kilogram car is traveling at a speed of 24 miles per second, or sorry, meters per second. How much kinetic energy does the car have? All right, who has that? What's the formula? KE equals what?
1/2 times m times v squared.
Okay, right.
Is the answer 14,400?
Let's see. So the first we're going to do is write down everything we've got. M is 1,200. V is 24 meters per second. And then our KE, our kinetic energy, is going to be in joules. All right, so we're going to plug everything in. Notice 0.5 is the same thing as 1/2. Yes, we all know that. Yes? Okay, good. All right, so here we're going to do the math. We're going to reach the conclusion. What did you say?
Not that.
345, 600. KMM over, is that SS? So that's going to be meter squared, second squared. And so we're going to see here that our Newton is kilogram per meter per second squared. So that is, the units at the end are Newton meters. And a Newton meter is called a joule. So our answer is the kinetic energy of the system, the car, is 245,600 joules. So what happened, Sudi, to your calculations? Did you not do your 2?
Oh, I did not do my 2.
You didn't do your 1/2. Just divide whatever you multiply by half, or multiply by 0.5. If you do it like this, you'll remember to put that 2 at the bottom.
Well,
What is the half? What exactly do you mean? Is that
Well,
divided?
because I did it like this, but remember, it's just our formula, David. 1/2 times meters. That's our formula. So that's where that 2 comes from. And the 1/2, but 0.5 is the same thing as 1/2.
Okay.
We just converted to a decimal point, because it's easier this way. Or you could just do 1200 times 24 and divide the whole thing by 2. We could try that. Alright, so that means it's a reasonable answer because a car has a lot of mass. It's a big car. Cars are heavy. Alright, so that makes sense that it would be such a large number. We might want to call it kilojoules by saying 345.6 kilojoules. I would move that decimal point over 3, right? Kilojoules, 3, that's 1,000, 3 zeros. You got a problem, David?
Yeah, I'm a bit.
Did the math not work out?
Yeah.
I didn't do this math. I just put the thing, this came straight out of the book.
I didn't square the 24 is what happened.
Oh, okay. Yeah, you gotta square the
You gotta
24.
square the 24.
And remember our order of operations, don't we do that first?
Yeah.
Okay. Yeah.
Can't
And then we
forget
can
little
multiply.
2.
Alright, and keep in mind this example is in your book, just like this. All written down in the book that way. Alright, good? Okay, what about throwing a baseball? Here's a kid throwing a baseball.
There we go.
That's hard to get it where you want to
You got it?
It worked.
Okay. Alright, so the baseball has a certain amount of mass. Have y'all played baseball?
I played backyard baseball.
I was about to say, what about softball? Because in the softball, the difference is the ball's a lot bigger. But I don't know about it. Does it weigh a whole lot more than a softball? A baseball's pretty heavy.
I thought it was lighter.
Because I got hit really
Kick-
bad.
it's
It's
good.
the softballs are heavy. They're
Heavier
not
than a
they're not
baseball.
soft enough.
Oh, they're not soft, that's
No.
for sure.
There's also kickball, which is similar, but not, but with a different, ball.
I think it's the way
Yeah, we're gonna be using a kickball kind of a thing today for our lab. Okay, so let's see, we're gonna be looking at this kid throwing a baseball. A baseball with a mass of 0.142 kilograms is thrown with a speed of 25 meters per second. How much kinetic energy does the ball have? Alright, we're just gonna use our thing right here. We're looking for KE, alright? So we're gonna say we have our mass, we have our velocity, and we're looking for our joules right there. So here we go. And we can do the 0.5. As long as everybody understands 0.5 means 1/2. Alright, we do the math. We do all our stuff. Look, our 24 times 24, that helped remind us right there about that, squaring that. And we get 40.896 joules. Notice the difference between the kinetic energy of the baseball and the kinetic energy of the car. Big difference, right? Because the car had so much more mass.
It says 25 meters per second. You said 24 in the problem.
Oh, interesting. They changed it to 24 for some reason. That's a misprint in your book.
See, I
Because this
told you I
comes
was
straight
right.
out of the book. These things right here came straight out of your book. Interesting. So we should make the book people aware of that. The larger mass means a greater kinetic energy.
The book was wrong. What is it? I was wrong. It's 3.3.
So if y'all want to switch that to a 25,
If you do it the way.
we have to redo the math, of course.
What, switch the,
Well, notice here, David, it said 25, but down here it
Oh,
plugged in
okay.
24. I didn't even notice that. Erebus noticed that.
I told you I was right.
What were you right about?
I knew it was a misprint.
You did.
Something was wrong.
You knew something was wrong.
Something was
This
wrong.
math didn't work. Something was wrong. Yeah. Well, remember, this is a brand new book, and that's one of the problems we have with the brand new apology books. There's mistakes that people missed. So maybe I should write to them and say, hey. All right, but now check it out. We're gonna look at a professional. That looks like a girl right there, but we're gonna look at a
It is.
professional pitcher. I don't know if she's real. Is she real?
I think it's girl.
The same baseball with the same mass is used in question B. Now is thrown at a speed of 42 meters per second. In other words,
That's a weak throw.
is it? What is meters per second versus miles per hour?
I don't know.
I'd have to do that conversion.
Oh, they said miles per hour. I was like, that's slow.
No, yeah, that's slow for miles per hour. For meters per second, I think it's reasonably fast. What's the new kinetic energy? Let's make sure they use the right stuff here. All right, so 0.142 kilograms. We had that from the previous question. 48 meters per second, and we're looking for the KE. All right, we're gonna plug everything in. We're gonna see that it's 163.584 joules. Wow, that's a big difference. Would you
It's
rather
still the
catch a
same.
ball thrown by a kid or by a professional?
A kid.
Same here. But remember, this all goes back to F equals ma, right? Force equals
Olivia.
It says 42.
mass
Look.
times acceleration.
Okay, look,
The bigger the mass, the bigger the force.
in the question it says the speed is 42, but in the problem it's 48.
You're right.
I
What are
told
we
you I was
missing
right.
here?
I knew I was right.
Is that another misprint or am I missing something? That is,
Misprint.
why would they have a misprint like that? That's
I
crazy.
told you.
Note the difference between the kinetic energy of the baseball in questions B
What's
and
real
C. The speed of the baseball
real answer
doubled,
is
but the kinetic energy,
125.244.
the speed of the baseball doubled, but the kinetic energy increased by a factor of 4. Because 163 point whatever is 4 times more than 40 point whatever. Okay, so we have a letter to write to the Apologia people.
We do.
Crazy.
Is this from the new book?
They need to apologize.
Yes. We're bringing it up.
Oh, the dad jokes.
All right, potential energy, remember, is the energy that potential means it's not moving, but it can. Okay, so I have a ball over here. This is a racquetball. You ever play racquetball?
Yeah.
No.
Oh, it's so much fun. So much fun. But you have to have a court to play. You have to have a court. All right, so this ball right now is experiencing potential energy because I'm just holding it still. But as soon as I let it go, right?
Well, you're shaking, so it's moving.
A little bit, yeah. Do I look like I'm shaking? So the two types of potential energy, it's stored energy. That's a blank. That probably means you need to fill that in. Okay? Potential energy is stored energy. It's ready and waiting, willing to go. We have gravitational potential energy. What's going to be the force pulling it at it? Gravity. Gravity. And then we also have elastic potential energy, which, by the way, when this hit and bounced back up, it bounced back up because it was elastic potential energy that bounced it. Does every ball bounce?
No.
No. Depends on what kind of material it's made out of, yeah? Okay, so our potential energy is here's a rock waiting to go off a cliff. Did y'all see those rocks that fell off? It was in Brazil or somewhere.
No.
It was like a landslide did you see, and people were in boats?
Yeah.
Apparently some of those people were killed. It's awful. But when you're in a boat and you see some cliffs starting to lose rocks, go away. Take your boat away. That's the thing. And people were watching going, "Ooh, that's so cool. That's so pretty."
Oh my god.
Not so much cooler.
At least they got some awesome footage out of it.
Well, it was kind of because people were holding their phones, and it was like I saw the footage. Yeah, I didn't. When everything hit, well, the people got inundated, so I don't know if those people were killed, but their phone was. Yeah.
But their YouTube
Because
went way up.
the water makes
A lot of
the
it's
rocks
like
makes the water
Are you dead?
waves.
Yeah.
Yeah.
They probably lost it at the point. Yes.
I saw this video of
Because I'm dead.
a guy who was on a boat and they were in like some snowy place, and the snow fell down into the water and created a large tsunami.
It was
coming
probably a glacier that was
Yeah,
falling off.
glacier.
Yeah, called calving.
down.
Yeah.
And it almost hit them.
Yeah, you gotta be
And
careful.
it died down right before it.
Okay, so that glacier was succumbing to gravitational potential energy and it became kinetic from gravity, right? But elastic would be with something that has an elasticity to it. Today we're going to be working with rubber bands.
Oh.
We're going to be shooting rubber bands, but not at one another.
Oh, I have to.
That's the best part.
In engineering, we made polymer bouncy balls. Like we made our own polymer.
Oh, how'd
and
that
we
work
made
out?
bouncy balls. They work pretty good. I throw my way after.
Did you have chemicals you mixed together?
Yeah.
Okay.
We use boring.
I got my family 3D printer for Christmas.
Yeah, we use like.
Yeah, me and my son's been printing some cool
Yeah,
stuff.
We have
saw
Did you
that.
see Alex stuff? Yeah.
He made a Pokemon.
Oh, we did. I don't know.
Hey,
what that is.
what brand is it?
I have no idea.
We made.
But I do know it's not filament. It's the other kind.
Is it good?
So far, looks pretty cool.
What's the
We like
filament?
we curdled some.
Filament is where you take the
Ooh,
string and
yeah.
put it in, and it does kind of a swirl
And the
thing. This is
vinegar.
liquid. Do you pour into it? So that's called. You might know what that's called.
Is it better?
My son thinks it is. I have no opinion. I'm waiting for him to make something for me.
Really?
Yeah, I have nothing for me yet. All the kids at church got something, but not me. Yes.
We got vinegar and borine and we like mixed that together and glue also.
Maureen?
Borine.
Boron?
Boron?
Boron. That's what.
Okay.
And then we just mixed all that together. We did it really fast because it was starting to
and then you have to put it in a mold of some sort.
we had to use, we also used dye. Then we had to pick it up with our own hands and just roll it.
Oh,
So
really?
it was, well, yeah.
Okay, did you wear gloves?
No.
Okay. No judgment. Yes.
So it's getting the stuff off your hands. And the
Oh,
table.
kind of gooey, yeah.
And the
Okay.
table.
All right, so now we're looking at our gravitational potential energy and our elastic potential energy. So, gravitational potential energy is related to an object's position above the Earth and the object's acceleration due to gravity. What's free fall?
What I wrote was when an object falls without gravity or air.
Just because of gravity.
Oh,
Right, if I throw it, that's a little more stuff to it, but I just let it drop, that's free fall.
dang it.
Only under the gravitational pull. Okay, so here we have this elephant, right? And so I'm guessing that we're wondering about the integrity of the little stand that he's standing on. Am I just our equation is this: PE equals m times g times h. This is for gravitational. So potential energy of gravitational equals m mass times g would be gravity times h, how high they are.
Is that Dumbo?
Could be. All right, so I put this in here because this is because of gravitational. You know what this is? It's called ski jumping. Okay, and they're coming down a big thing and then they're just flying, right? I put this in because you know what's coming up in a few weeks? The Winter Olympics. Yeah, but they're in China, so boo. But we're going to be going anyhow. So we can watch people like this. But the book is talking about diving.
Just trying to get winter. Snow?
Apparently.
Huh.
They go pretty far to the north up there, yeah. So here we have a diver. This would be Summer Olympics, right? So the potential energy of a diver. The diver has climbed on the ladder up to the diving board, and he's under gravitational potential energy, right? So he's standing there and he's going to dive off. Suppose a diver that we just saw is at the top of a 10-meter high diving platform and has a mass of 80 kilograms. What is his potential energy relative to the ground? All right, so we're going to say that we have these mass is 80 kilograms. We know gravity is 9.8 meters per second squared because that is a constant, right? That's a constant. You remember what it is in English units? It's 32 feet per second squared, right? But we're using metric because it's science class. So 9.8 meters per second squared. 9.8 meters per second squared. Okay? Our height is 10.0 meters, and we're going to be calculating our potential energy. All right, so here we're going to plug everything in. Nice. It's just a multiplication problem. So when you take your quiz for this one, you will definitely want your calculator, and yes, you may use your calculator. All right, so here we're going to punch everything. Don't forget units. Oh, notice the unit. 7,840 kilogram meters squared over second squared, which is now called joules. 7,840 joules. Just as with kinetic energy, these units are equal to Newton meters, and a Newton meter is equal to a joule.
You got it.
All right, that's part A. The potential energy of the diver is 7,840 joules, or 7.84 kilojoules. All right, after he dives, the diver climbs out of the pool and is standing on the ground.
I thought you said died. I was like,
Dives into the water.
I think he's died.
He's standing on the ground. What is the potential energy now? Okay, so I put these pictures up. These are famous American divers, and they're standing because they were standing on the medals platform because they won medals. This is Greg Louganis. He's older now. He's not as old as I am, but he's older. He doesn't compete anymore. Holding his gold medal. This guy's name is David
Hasselhoff.
Boudia.
you don't know my name.
B-O-U-D-I-A.
These people
And this is Krista Palmer. Krista Palmer just won the bronze medal in this past Summer Olympics that were in Japan, and she wasn't expected to win anything, and she comes away with the bronze. It was really awesome. Did you have a question? Okay. All right. So since the diver is standing on the ground, his height above the ground would be 0. Therefore, his gravitational potential energy relative to the ground would also be 0. Standing. I'm already on the ground. Nothing's pulling me down. Question?
It would just be 0.
0. Yeah. Yes.
Duty's awesome at this.
Zudi's awesome. You're at the mat, or are you still finding?
No,
do I
I
have?
just got
It could be an error, because of this book.
Could be. Yeah,
No.
it could be. Yeah, maybe
Right.
I'm exactly wrong.
Now, elastic potential energy is related to an object's ability to spring back to its original shape when stretched or compressed. So a compressed would be like a spring that you push down. Elasticity of a rubber band is what we're gonna be seeing about, see, because it can compress back to, that was pretty far, okay. A bow is a good example of this type of energy, right? A bow, here we can see somebody shooting the bow, boing. Pretty good.
They have better bows than that nowadays.
That looks almost like you could have, no, that's like a real bow, okay. I was thinking maybe it was handmade or something. Maybe, when you were a little kid, didn't you make your own little handmade bow? An arrow?
Yeah.
And the arrows go flim, flim, because it's so good, yeah. So,
My brother.
all right, check this out. This is a golf ball. Check it out. When it hits, see how it deforms that? Because of the elastic potential energy there. So if I threw this ball really hard and were able to videotape it, it would even compress even more than a golf ball. Because golf ball's hard.
Yeah.
Yeah. So that's pretty amazing. It does that. Question?
Oh, no, I was just about to ask, like, why does it do that whenever it's so hard?
I know, it's because there is, you know, and remember, law number 3, for every action there's an equal and opposite reaction, right? So it's hitting the wall's hitting it back, that's why it bounces back.
So they're fighting them?
It's elastic. Now if I threw something like clay at the wall, splat, it wouldn't bounce back, because it wouldn't have elastic potential energy.
So
yes.
the reason the ball lives like that is because it has elastic potential energy, but also has those atoms are tightly packed and they get spread out.
So the material that's made out of, yes, is an elastic material. Not as elastic as this one, because I can't do that to a golf ball. But also, if you think about it, a professional golfer, when he hits the ball, it also squeezes it and deforms it.
Yeah.
And then it through
Because
the air.
it moves the atoms around.
Oh, sure. Yeah, absolutely. I don't know if you've ever opened up a golf ball. I wouldn't do it. It's like wrapped with a bunch of rubber bands. You know this? And in the middle, I think there's some fluid of some sort, and I think it might be acidic or something that might hurt you, so you have to be careful there. But they're really unusual. Now, this ball is hollow on the inside. It's just made of whatever it's made of. Rubber. Yes.
Are longhorns horns hollow, is that? Or are they full of?
Longhorn cattle.
Yeah.
I'm gonna say they're not hollow.
Because I've.
But if they die,
Mm-hmm.
then it might hollow out, kind of like a bone would have something in it unless something's dead and it hollows out. You know what I'm saying? So it might be that one. Because I know that other horns they'll use to, but I think it probably has marrow or something.
I saw some on the way.
Some longhorns?
Yeah, there's like a, you know Rosinki.
There's some right here on this corner lot.
Rosinki Christian Academy?
I don't know where that is.
It's not Rosinki, obviously, but if there's like a road, there's like an intersection, you go down the road. We go down that road every time we get here.
Okay.
I see my brother's school, and we haven't seen them before, and they're new. I was like, oh, that's new, because I haven't seen them.
Very Texas.
Yeah.
Okay, other specific forms of energy. Is this a set of blocks, a little fill in the
Yeah.
blank in your book? Okay. We're just gonna write these down. Mechanical, it's kind of energy. If you ever look at your engine, the engine's moving, isn't it? Engine of a car, when it's running, it's moving. That's mechanical energy. Thermal. That's heat rises, right? Heat rises. So if you've ever seen a pot of water boiling, those bubbles are moving, yes? Remember, energy is moving unless it's potential. Chemical energy. Chemical energy, a glow stick would be a good example. I break a glow stick, what happens? It starts to glow. There's chemical energy moving in there. It's moving around. All those atoms are moving. Electrical energy, it's right here in these lines. Electrons are moving through a
Does it matter
wire.
what order they're in?
Nope. Electromagnetic energy, EM. Remember electromagnetic, if I shine, if I run electricity through a wire, it's going to create a magnetic field. If I'm able to move a magnet around, I can create an electric field, which is exactly how we get electricity here. Sound is a form of energy. It's moving through, by way of waves through the air. It's moving from my voice to your ears right now. Okay? It's got to have a medium to pass through. Nuclear. Nuclear energy is where we have certain elements that undergo radioactivity on their own. They fall apart spontaneously because they're unstable. And we can take that to boil some water. And if I boil water, I can make steam, which moves. And if I can move something, I can make energy. Or I can harness it. All right, the law of conservation. Wait, this is at the bottom, below lab.
Yeah, it is.
Okay, the law of energy conservation. This is super important. This is called the first law of thermodynamics. And it states energy cannot be created nor destroyed. It can only be converted from one form to another, transferred from one object to another. Usually we say energy is neither created nor destroyed, it only changes form. Here we see a firework, right? It had potential chemical energy. We lit it. It went through the reaction with oxygen and it exploded. Boom. And same thing here. Did we saw this? Remember I brought this to you? Did we do this before?
Stress me out.
Yeah, called a Newton's cradle. It stresses you out. It's supposed to calm you down.
No.
Oh, okay. It's supposed to be very calming. And then this one as well. Watch it's like a roller coaster. It's going to go from the top to the bottom. So it went from total potential energy to total kinetic energy. Whoop. Right there. All right, that's all under the law of conservation. Now it's lab time.
Yay!
All right, so we're going to do a couple things.
I'm wearing a sweater.
And depending on how it goes, we may have to leave the room and go elsewhere. Okay, we're going to start with a bouncy ball.
I'm wearing
Can I do the bouncy
a
ball?
sweater and
Really? I'm going to bounce it to you.
Oh, I just see that.
Supposed to
Gracie,
catch it.
I'm sorry.
supposed to catch it.
For that.
But who's catching it?
Casper.
David will catch it.
Do you know Casper?
The ghost?
Casper, it was supposed to bounce the land on the table.
Casper the friendly ghost?
Yeah.
I do.
Ooh.
Okay, so here's what the lab is. Do we have 2 pages for lab or just 1?
There's an additional page.
Oh, there's an additional page.
Well, that's a blank page.
That's I asked for those, you know. For additional pages. And they gave them to me. Very happy. All right, we're going to do 2 things.
I like the additional pages.
So the first thing we're going to do is we're going to compare 2 balls.
Which
Okay.
lab is the longer lab? 'Cause I can write in the one where you can write.
You know, that's a good question. The longer lab is the rubber band lab.
Because we shoot each other.
You do not shoot
That's
each other.
what it's the stat.
I'm wearing a sweater and jeans. I think it'll be fun.
All right. Because supposedly, with the energy of a rubber band, we're going to try to graph it. Is there a little piece of graph? Is there any graph on your book?
No, but you can make a graph.
Yeah, that's a bummer though.
No, they takes.
Keep
On
keep
that-
turning and see if there's a graph. If a graph
On that
comes
additional
into
page, you have
vision.
more.
Nothing?
No.
Huh.
Yeah.
Okay. Well, we're going to start with the ball bounce. So on your empty page that says additional page, or this is left blank on purpose, or whatever it says, put in ball bounce. Okay. It says we want to do it where there's a high ceiling, but I don't see why. We need a large ball, which I have here, which I would call this a 4-square ball. Y'all ever play 4-square?
Yes, I love it.
This is a really soft 4-square.
Playground.
That's a
I
big one though.
love 4-square.
That's a big one.
Yeah. This is one I sent to my son at college to teach all of his Arkansas buddies how to play 4-square because they'd never heard of it. Arkansas. All right, so we have a big ball and we have a small ball. And what we're going to do is this, okay? We're going to take a yardstick, which I have. You're going to drop the basketball from the this red ball from the height of 1 meter, and we're going to try to get an idea of how high it bounces all by itself. And then we're going to use this ball to do the same thing, and you're going to make a guess which one is going to bounce higher. Any guesses?
The little one. The big one.
Little one.
Little one, little.
Okay. And then
Actually, I'm not sure.
then we're gonna put this on top of this one and bounce them both together. How high did the balls bounce in each instance? How can we explain what happened in terms of mechanical energy potential and kinetic energy? It says here the tennis ball has more mechanical energy when dropped with the big ball. Okay. All right. So what we're gonna do though is we're gonna drop it from a height of 1 meter. So this is a meter stick.
Oh, we used to have one of those. We used to
Yeah.
make the
It's
house
a little,
with it.
right?
So it's about 3 feet. That's 1 meter. Okay, so what I need then is, y'all have to get to a place where you can observe this, and I need someone to hold the meter stick
I
and
got
drop
you.
the ball.
Hold it.
Okay, then you're gonna drop the ball.
Oh yeah.
So hold the meter stick. So I think what we want, Josh, is we're gonna make sure that the bottom of the ball is at the top of the meter stick. Okay, everybody needs to watch and try to get an idea. What can they see? Okay, about like when it gets to its highest spot. Okay, first question. Do you think it'll bounce higher than the meter stick?
Yes.
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 Wait, you're just gonna drop it. You're not gonna do this. If he drops it, will it go higher than the meter stick?
No.
No.
I think it can't. I think it can't. Right?
I don't know.
You don't know.
We'll see.
I don't think it will. Okay. Now, if you do this, yeah, it'll do that. Okay. So, and then after that, we're going to drop this one from that same level, which is, right at the top of that.
So the bottom of it,
At the bottom of it's going to be at the top of the stick, but to the side of it, okay?
Wait,
Because
okay.
I don't want to drop it in front of it because you need to be able to read where it went.
We're not dropping it from the.
No, we're dropping it 1 meter.
Then it's not gonna go higher. than
Right. It can't. Right. Okay, so let's do this one first. Our guess is which one is going to go the highest. Okay, so just make sure it doesn't hit the stick because it will influence it.
Your brother.
Okay, 3, 2, 1, go.
That was fast.
It came, the top of it was about
Yeah.
right there.
Yeah.
Right?
somewhere around here.
It was high. It was. I would say.
You think it went above it? Let's do it again, Josh.
A little bit above it.
Okay, David, hold it
What do
again.
you say? What are you watching?
Oh, keep in mind the bottom of the ball is at the top of the thing. If we dropped with the top of the ball at the bottom, it wouldn't come to the top. So it could go past it. So you want to stay right to the top?
Yeah, right.
All right, now you're going to do this one. What's your guess?
A little
Higher?
bigger. Higher.
Higher, okay.
Not higher.
Not
Remember,
high.
the bottom's going to be
Less,
at the...
way less.
Oh, okay.
That's
Ah,
it.
yeah.
So could you tell where it went, though? Did we get a
where's
number?
that?
Did we get a number?
At 10, where that
So-
10 is.
So, hey, Josh, do it again, and David, I want you to put your finger where you think it
At that 10.
came up to.
I like that 10 and a half
27.
mark. It looked like the 10 and a half mark.
Is that where they are?
On the 32.
No, they're on the 30. They're on the 13-inch mark. I say.
And you say it didn't go that high?
I say. I say it was higher than that.
Oh, it went higher. Are we upside down?
Yeah,
Are we
we're
upside down?
Oh yeah, we are.
Oh, we're upside down. Okay, let's not be upside down. Okay, let's do it again, buddy.
Like that, yeah, a little bit higher than I say. I went to the 30.
Yeah, 30 to 29.
30 to 29.
Okay, and that would be centimeters.
No, that'd be
No.
inches.
That is
that's in
inches. So where'd you say it was? So 76 centimeters.
And then the other one that's like
76.
right there.
Like 89 centimeters for the red ball, right? Now, we're not done. We're not done, David. You gonna write your data down? Now what you're gonna do, Josh, is you're gonna hold the little ball on top of the red ball, and you're gonna drop both of them at the same time. What do y'all think's gonna happen here?
The ball will just like
The-
drop
The
off.
smaller ball will go
Ready?
higher because of
Because the red ball.
Okay, I'm ready whenever you
The
are.
ball happened
Whoa! Remember, was that the first day when I brought that little thing? I dropped it in the ball, but
Oh,
I
I
couldn't
think
get it to work very well. So what happened there? That was not quite expected, was it? We maybe should have had goggles on. I'm looking at you, Eliana. We could have smacked you in the face with that.
That was funny.
Yeah, at least it wasn't me. Mia got it.
Wait, what happens
Again?
if the big one?
Which one?
Well, only if we put goggles on.
What happens if the big one's on top of the smaller one?
What do you think?
It's gonna smack.
Don't work.
Okay, should we put
Oh,
goggles
the
on?
little ball's gonna turn down.
It fell out.
What, did it just fall?
It just fell out.
It just kind of shot out.
Yeah, it just went out from underneath it.
Bring some goggles in
See.
here.
Oh.
It just went that way. Ah.
Thank you.
Lauren, I get an excuse on this kind of stuff? Lauren, Lauren, I get an excuse on this kind of stuff because I had to wear
Yeah,
glasses.
like your eyes will.
I'm not for messing with chemicals and I had to wear it.
Josh, can I drop it?
I know some lady that.
You forgot somebody.
Her eyes.
No, I just didn't have
I
it. Okay, so what are we doing? We're trying to do the first one again or the second one?
gotta go do that.
Okay, so we don't have to worry about this at all.
She was holding on to it.
Oh, got me. I should put my
That is it.
glasses on.
Also,
I should
Alright,
like
now
the
put
camera.
the little ball, put the little ball on the top.
we should have
Okay,
one
y'all,
off.
it's the blue ball's gonna go a distance.
How?
So
So she was
green,
a
whatever.
mountain woman?
Guard your.
She had to like stick with something.
Alright.
Like diarrhea or something like that.
Okay,
And then, like,
so we
like,
understand what's going on there. Let me read it to you.
Fell and like a stick went in her eye and popped it out. Right?
The little green ball.
And she was like 30 miles away from the city.
Okay, listen. The little green ball had more mechanical energy when it was dropped with the red ball than it did when dropped by itself. Why do you think that is? Well, the tennis ball, the red ball, the green ball, received some elastic potential energy from the other ball when they were dropped together. That extra elastic potential energy converted into more kinetic energy, allowing the small ball to bounce higher than it did when dropped alone. It also was able to bounce higher than the basketball did, the red ball, when dropped alone because the the green ball, it's a racquetball, mass is smaller than the mass of the red ball. So that increased kinetic energy but smaller mass allowed the small ball to reach a greater speed and so a greater height than the big ball. Pretty cool, huh? Okay.
How many centimeters tall is a stick?
It is 91 centimeters tall. Does that look like it's got a curve in it to you? Maybe not. Maybe it's just an optical illusion. I need to hand these back to people.
Uh-oh.
That was my microphone on. I am still recording actually.
Oh, we heard this entire thing.
Yeah, yeah.
Hi, John Mark.
Hey, John Mark. You could have stopped listening a while back.